was like temporarily down, or it's like it wasn't submitting jobs.
I have this kind of problem for several weeks, I guess.
Oh.
Like previously, I request 48 hours for the images,
Mm-hmm.
and actually, last calculation stops at 5 hours.
But it's the, it keeps running though.
Yeah.
Take some data if we
I had that problem with a couple of my jobs as well.
Really?
I feel like I vaguely remember having that happening for mine. I can look through some bit like directories, but I think I just resubmitted it and then it.
I haven't noticed that in like 2 weeks, but I saw that for a couple of my jobs. And yeah, all I did was resubmit it and it worked fine.
What kind of system? Like, what model?
I guess it doesn't matter which model you want. Because I tried different models like slab, molecule. I have all of them.
And in the slurm it just says can continue S run company.
thank you for a good one. Your there's a couple of
I'm good.
So let's listen something about David's research and provide him cooperative, constructive feedback in writing. And, there's an uncertainty with funding for Senegal, but it is so nice meeting that we should keep it in mind, and for awards for those who didn't got them in the past. It's better to think of submitting applications a little ahead of time. Just good insider signal that the formal deadline is like December 31st, but those that will be submitted before like December 10th will be top of the pile. So we should have two topics. Right, one of electronic state dynamic in the two-dimensional closed and proper perovskites, or maybe their modifications. Now, one of David knows what they are.
Most of them are beyond Jacobson, but
Okay. Outstanding speaker in the outstanding meeting. David Grobner will present research about cutting-edge subject. Yeah? And if you start with a little introduction to remind us, will be appreciated.
okay, apparently now it's working. So I'm working on a layered perovskite materials, which were, when I say layered, what I'm indicating is the amount of perovskite layers in my material. So here I just have a general perovskite model. And then what I'm looking at specifically is a 2D perovskite, which is our perovskite layers indicated here by the diamonds, separated by a material that causes them to form layers, which would be coming in and out of the screen here. And the reason we're looking at these is they have shown that they have an better stability than the 3D models, which increases with smaller perovskite layer sizes. And this decreasing the perovskite size also affects its optical properties.
Mm-hmm.
And then what I'm specifically looking at is photovoltaics, and what the photovoltaics is it's a method to convert solar energy into electrical energy, and it works by having an active layer, which in my case would be the perovskites, and then you have something, a hole or electron transport layer that allows the charge to separate, and then anodes and cathodes around that to collect the charge and make a circuit. So my printout is sitting on the corner there.
Oh.
You can have my copy. So the one way that we can evaluate the photovoltaic materials is its efficiency, which I have outlined how it is, and what we're looking at is the ratio of the red square and the blue square here. And
What is MP? Maximum power?
MP, yes, MP is maximum power. MP is max power, OC would be open circuit, SC would be short circuit, FF would be fill factor, and P in would be the input power.
So the red square right lower edge touches a curve. What is this curve, where it comes from, and how to modify it?
So this is the current voltage curve, IV curve.
What are the options to modify it?
The
Is it the same for each material?
curve, no, it's different for each material.
So by just trying different materials and interfaces, the curve may improve.
Yes, and so the goal would be to have the red square and the blue square overlap as much as possible.
So if this IV curve will be almost rectangular, it
That would be the best situation.
okay. Is it experimental IV curve, or what?
This is just a schematic.
But generally, is it possible to compute it, or only to get it from experiment?
My knowledge is generally experimental.
Sorry. Sorry, go on.
Go ahead. And know that David needs to depart before 5.
Oh.
But
I still teach today yet.
keep
Oh,
us
So what about the just as overlapping to a square, or what about the dimension of the square? If we is our goal.
So the dimension of the square would indicate the maximum total, where the efficiency is related to the ratio.
Oh, okay.
So the bigger the square, the more we could get out of it. The bigger the blue square, the more we could get out of it. And then the bigger the red square within the blue square, the more of that potential ability we're getting. Does that make sense? Yeah.
So how does your active layer relate to all those parameters you have? Your current and your voltage?
What do you mean?
So I guess like current is like current that flows through the entire like
So-
architecture.
Yeah.
So I would suspect like your active layer has a little bit to do with the overall current, like the ability to give its charges to the transport layers.
Yeah.
But then, I guess how can you vary the voltage with your active layer? Because that's where most of your power is
Yes.
going to be coming from, with ideally minimal losses.
But it also depends on the alignment and also in
Right.
attachment with their own.
Right. It depends on like if you could find ideal like transport layers
Mhm.
to minimize voltage losses.
You ask more questions than answers. So, what is? I continue your embarrassment. What is Ohm's law?
Ohm's law is voltage equals current times resistance. Other way around. Current equals voltage times resistance.
So, connection between voltage and current is linear,
Yeah.
and you are showing some curvilinear. Why? So you are fighting with Ohm's law, right?
Yeah.
Because Ohm's law is for single material and you have interfaces.
Okay.
And your photovoltaics is photodiode. And curvilinear is photodiode. How would this curve change if there is no irradiation?
If there is no radiation, there'd be no current. We get the
At zero voltage,
Zero
there
voltage.
is no zero current. Same as in Ohm's law. And please check around if everyone who was asking questions is satisfied. If not, answer. If yes, continue.
So how can you change the voltage with your active layer?
have greater excitation. Or increase.
Let's write it down, this question, so that David answers it later. We'll
Yeah.
try now, but how to
Or increase the rate of charge separation.
change VOC is choose active layer. Is there, I do not want us to be tortured. Is there a connection between gap or between energy of Homo and Lumo of active layer HTL and ETL and the VOC?
Yes.
Okay, enough. Next time you will explain what is this connection. Compromise. Let's keep going.
So here I just have some quick data that shows that as you change size, you would adjust see that the absorbance and emission changes as you, so with the smaller size, it's blue shifted, and larger size, it's red shifted.
Okay. And maybe it will affect the open VOC as well.
Yeah.
Because there is definitely some connection between.
Some other ways that could affect it is if you were to set up your active layer with multiple sizes, you could absorb a greater range of the spectrum because the sun is giving us white light. So here I am showing my n equals 1 beyond Jacobson perovskite. So if we look at it, we have our perovskite here, and then this chlorine will repeat here. And I have them separated. My organic ligand is a propyl diammonium ligand. So in this situation, I'm using the ammonium from my organic ligand as my second cation in the molecule. And here I have my density of states, and we see that there's about a 2.6 EV band gap.
So is this chlorine, that green stuff?
So the green is chlorine, the brown is lead, hydrogen's white. The dark blue is nitrogen, and the light blue is carbon. And later ones, if the purple would be cesium. Although this one doesn't have any, but I used purple for cesium.
So what is this floating atoms on the top? I don't get it.
So this is periodic in the Z.
Oh, okay.
C. So this one will be up
Oh,
here, and
okay.
that completes the diamond.
So these 3 atoms from the another cell, maybe, right?
Yeah, so
Oh, okay.
there'd be another cell here, and then this chlorine,
Oh, okay.
there'd be a chlorine here, and it would make a diamond structure. So here I have the Homolumo visualized for the model, and the Homo is focused on the chlorine atoms, where the Lumo is on the lead.
How is this image is periodic? It's kind of like the top red bubbles. It's
So that would be connected to this chlorine down here.
not look like that. So you see there are a half fragment of this red bubble.
Yeah.
Something is missing.
I remember that being on the chlorine down there, but that little bit right there is what you're talking about, right?
Mm-hmm.
Do you use orthographic or
It's orthographic. It's not
not perspective?
not perspective.
Because perspective sometimes removes parts of orbitals.
I changed that because it's easier for me to move it.
Well, next time you look at them, you can replicate cells.
Yeah, I can. I was when I was looking at it without the orbitals, I was replicating to see how they stacked, but I didn't replicate it. Didn't show the periodic with orbitals.
But what you're showing, Luma is p orbital on lead.
Yeah.
P5 or P6?
I think it's P6.
Okay. And for HOMO, it is P2 on chlorine.
Chlorine should be 3,
Okay, whatever you tell.
I think. I'd have to look that one up to be sure.
And you may mention it if you intend this figure later to go into something serious.
Okay. So here I visualized HOMO minus 19 and LUMO plus 39. And we see the same general trend as we see in HOMO and LUMO, except this one. This has some density on the carbon.
Not the same. Maybe about for occupied.
Yeah, for occupied we see similar. For the unoccupied, we see some density on the organic.
So 5 plus 39?
Because that's the one that I looked at for my next slide, which my next slide has some issues.
Does this one has largest oscillator strengths?
It was a good oscillator. It was in the top 10.
Okay.
I made sure it was in the top 10, but I just used numbers that I had in the program when I did it because I was getting odd results. So if we look, there's a excitation around 4.4 EV, but then it drops very quickly to right around 0 EV. In the picosecond time range.
You're not showing absorption spectrum, but can you show it next time?
That is the absorption spectrum right here. Another thing I'm having issues with, and I have no idea how that happened.
How many transitions you included in this?
What's the right suggestions?
If I remember, it was in the 800 range.
800?
And I redid this for my other models, and I redid it again trying to prepare.
Have you looked on the oscillation strength?
As far as I can see, there's nothing wrong with my
No, I mean
oscillation
maybe
strength.
one transition has a unexpectedly unrealistic oscillation strength, and that's make everything insignificant maybe.
I suppose that's possible. I need to go back and check.
Because the sharp narrow peak is like.
But I'm seeing this with all 4 of my models
Oh, okay.
as well. This
You may
peak
want-
right around 1
Uh-huh.
EV.
You may want to bring up additional slide with values, like part of the
The
oscillator.
OS strength file.
Yes, and arrange it not, you can sort it
Yeah.
based on the transition energy, not based on the value of oscillator strengths.
Okay.
Also, you may consult with both Yoon and Aaron. There are there are several versions of the code for oscillator strengths. One of them, which is intended to compute emission, includes intraband transitions from occupied to occupied and from unoccupied to unoccupied. And
Okay.
such such type of oscillator strengths is not intended for absorption spectrum. Just consult with all of us or one of us. And next time show part of the file so that we recognize it.
Yeah.
Okay, thank you. More suggestions?
No, that was my thought.
So here's the n equals 2 model, and here the purple colored are cesium, otherwise all the atoms are the same as in the previous. And apparently this is not the one where I had the band gap energy written down on the slide.
So I missed your introduction, that's why I'm asking. N equal to 2 means the 2 layer of...
So n equals 2 means that I have 2 perovskite layers.
Oh, okay.
2 layers rich with lead.
No.
Yeah. So the easy way would be I have two layers that include lead. It's the easy way to look at it and see that. This was about a 2.4 EV band gap. I apparently didn't write down the exact number in this one.
How many?
About 2.4.
So the trend is healthy.
Yeah.
Okay.
The trend is it's the band gap is decreasing as we go bigger, which is what we would expect. And for the n equals 3, we see about a 1.8 band EV band gap. And I did not include the absorbance files or absorbance spectra for these because they look identical to the n equals 1 model.
It could be, do you use the same data for computing emission in the MATLAB code and for making the absorption in command line?
So
There are several versions, several executables that generate file named oscillator strings.
yes,
But they are not identical.
No.
They're not labeled well. And one is intentionally made only to generate data from MATLAB to get emission, and another is
I was not using the same OS file or file to generate OS
okay.
for my absorbance as I was the MATLAB ones. And in the n equals 4 model, there's about a 1.7 EV band gap.
Do you have a plan to add a slide with
What's
gap as function of number of layers?
Gap is, yes, I do. I started to put that together, but
Basically, you could do it right now, just opening Excel and putting this data.
I started to put it together, but I noticed an issue with one of my files when I had done it, and I hadn't fixed it before that point.
But we can do it right now. So 1, 2, 3, 4, and another will be gap 266, 2.4, 1.8, 1.7.
Is the mouse fighting me?
Okay, and just copy paste it into the slides. Later on, you should fit it into 1 over r, 1 over number, or 1 over number squared, something like this. It's not linear. It's not expected to be linear.
No, it's not.
But let's just copy paste the image into slides and go forward. Very good. And what is expected? How should it depend on the number of layers?
It should be dependent on the reciprocal square.
Mm-hmm. So 1 over this, 1 over squared of this number.
Yeah.
So if you remove 1 layer and keep 1 layer, 2, 3, and 4, it will approximately fit into 3 lines will fit into 1 over n squared.
Okay.
Okay.
So here I'm looking at a model that's completely inorganic, and unlike the earlier models, which would fall into the Dion Jacobson category, this one is a Ruddleston Poplar face,
And
which
what is the experimental motivation to look into inorganic things?
So the original motivation was to compare the hybrid model with the inorganic model, and it was found that the hybrid organic model, the organic ligands act as like an insulator, which we do not see in this. At that point, I then started examining the different sized perovskites.
But is there hope that fully inorganic do not degrade with time?
That would be the reason to look at them.
Okay.
So, this has a slightly different color scheme than the one I was using earlier. These lighter purple are iodine, where the dark purple is cesium. And the chlorine is green and the lead is gray. And here we see about a 1.5, 1.6 EV band gap, which compared to the last time I talked would indicate that the last one I had the wrong DOS for, because last time I appeared to have had spin restricted DOS instead of the spin orbit. So if we look at the occupation for these, we see that in the hole in the electron that there appears to be degenerate states, both where I excite and at the band gap.
Which model?
This is the inorganic model.
Okay.
And one feature is that at the the hole seems to relax primarily to Homo -1 rather than Homo, or more to Homo -1 than to Homo. And
So this signature, it's a signature that you are doing calculations with spin orbit, right?
yeah, this is spin orbit.
The dynamics are kind of interesting because for both your hole and your electron, you have like
Oh,
for state 6 and 7 for your hole,
6 and 7,
or 8 and 7.
8 and 7.
So you have 2 peaks up here.
Yeah.
And then, I didn't. Okay, there are pairs that
They
are
yeah.
identical.
Looks almost identical.
And you see the same in your electron relaxation too. So it's like there's a faster and a slower,
Faster and a slower path.
yeah, to get to those states.
You do see that there's a shoulder here as well.
Mm-hmm. So so it looks like it slows down.
Which, at the angle I posted or put these on here, it's a little hard to see exactly where that lines up, but it looks like it lines up with the second peak.
If you want to flip to the next, you may ask, are there any questions? If no, I'm going forward.
So then here I have energy relaxation, and we see that around 1 picosecond is when it relaxes to the band edge. But we see in both the hole and the electron that they have a population below the band edge for a significant time, and in the electron case, we actually see a shoulder in our path.
Are there questions to David on this lighter figure on the left?
Oh, there's a lot of questions.
Let's discuss. I think there are generous 20 minutes before your class starts.
Yeah.
We can use part of this time for discussion.
So these are the same dynamics as for your last slide.
Yes.
Could you copy and paste the last couple?
So this would be the hole, that would be the electron, if you didn't follow how I pasted.
So it seems for both of them there is very fast relaxation to the band edge.
Yeah.
But then there's like a separate population that takes like a different route or a slower route to get to the band edge.
And we see that there's population. You can actually see it all the way out to the end of the graph here.
So those are probably like your bigger, like your slower humps, like 6, 5, 4.
Yeah.
I will try to answer instead of David. maybe it's a hypothesis to check. There are several resonant frequencies of normal modes. One is by good or bad luck provides channel for immediate relaxation from this Homolumo plus 8 to Homolumo. So like high energy frequency like CH oscillation.
Like if it's on the surface.
Like this. And another is small portions and this to sort of low frequency. So there are two simultaneously active channels of energy dissipation and they are competing. If this calculation has no errors.
Which is another question.
It's just healthy attitude to be a little suspicious.
But this is an inorganic system, right?
This is the inorganic.
There's
Inorganic,
no,
yeah.
no CH.
No CH.
No carbon, no nitrogen, no.
Are there any atoms that may give high frequency of oscillations?
This has iodine, lead, chlorine, and cesium.
So
Chlorine,
chlorine is the lightest.
Chlorine. Yeah, that's it.
It's to be explored. One day you may compute normal modes and compare transition energies with their peaks.
Okay.
More questions on this image? I do have a couple of strategic, not about contents and quality of this figure, but more about another 200 figures like this that you are going to generate in the next couple of weeks.
Okay.
So the figure is beautiful.
Yep.
It's your credit. But in the paper you cannot put 200 figures.
No.
Is there a way to summarize content of this figure in one or two numbers? What is the main message of this figure that was not available before you completed this image, before you completed this calculation? And you can just finger point the thing that you are thinking about.
So what numbers does MATLAB spit out at you every time you do a calculation? On the other hand, this is happening in time. So it's a way to characterize how fast.
Autocorrelation frequency?
Not correlation, but so like, instead of using time, like how to.
We're looking at the rate then?
Mm-hmm.
So rate of electron relaxation and rate of core relaxation. Can you, with laser pointer or with finger, show where it is? So this is expectation value of energy as function of time.
Yes.
But one can extract rate out of this curve.
Yeah.
So basically it's a point where the energy drops drastically.
That one.
Yes.
That one, and similar for the electron.
So it's time, lifetime of excitation or relaxation rate. It's a number.
Yes.
And anytime you run the code, it, as Aaron tells, it spits on you.
Mhm.
It shows this KE, KH.
Yes.
What are those numbers for this example? Just approximately. Where is 1 picosecond on the x-axis?
The 0 mark.
So your relaxation happens quicker than 1 picosecond or slower than 1 picosecond?
Right around 1 picosecond, looks a little quicker.
So it's like half picosecond would be good estimate for human eye, right? So
Yeah.
for this excitation from Hom-8 to Hom+8, and for this model, the rate of electron relaxation, whole relaxation is around 1/2 of a picosecond, the time, and the
Okay.
rate will be 2 inverse picoseconds, right? So the question, how this number depends on the model. Would it stay the same if you explore your organic 1 layer, 2 layer, 3 layer? Will it be the same 0.5 picosecond for relaxation time? You cannot say before you try. We can only guess. Maybe it will be a little slower in thinner models. How does this relaxation time depends on the excitation energy, on your choice of Homo minus something to Homo plus something? Will it stay the same or change?
It'll change.
Okay, then one may want to repeat it for each system for different excitations and tabulate these numbers. Like, if you have 5 systems and you do 40 runs for each, it will be 200 points. Well, maybe not as cruel, a little less, but now it's if we do not, if amount of suspicion is within threshold, then you are in the productivity stage to generate data.
Okay.
And this dependence of relaxation rate on other parameters like size of the system and excitation energy is a unique information that you are the only person in the world who can provide. So it will be the main product coming out from your calculations.
Okay.
Anything else you want to add to your slides? I apologize, I cut you in the middle of the, you didn't have chance to explain the rightmost if you wanted to.
So here we are once again looking at the excitation energy versus time, and we do see once again right around half a picosecond that there is a drop from 2.2 EV to 1.4-ish EV, but we see in the material that there is still higher energy excitation for a longer period of time.
Good. Conclusions. Written or verbal?
Apparently verbal, because I
Okay.
apparently didn't write. So we do see in the hybrid model, we do see that there is a decrease in band gap as we go to bigger layers, which is expected. However, I've been having some issues calculating the absorbance with them, and the electron dynamics I have appears to have something wrong with it as well. Where the inorganic model has some interesting features that should probably be looked at.
And I look forward to compute dependence of relaxation rate on parameters. Right?
Yeah.
Okay. Please join me in thanking David for a very interesting presentation. Last chance for more questions. 1, 2, 3. If there are no more questions, I thank David once again. Please do not erase because you added.
I was just
and
bring up the documents.
collect the feedback if any, and review your tabs if you need to for more energy. And today is the two-dimensional day. David was presenting on perovskites, and Fatima will present on two-dimensional graphing.
I'm going to talk about magnetic field driven dynamics of graphene. Here we can see a graphene. It has hexagonal lattice structure, and each graphene atom has 4 electrons. Balance band. 3 electrons make pi bonds with 3 neighbor carbon atom, and 1 electron is just 5 electrons along the jet. Here is the motivation. So we know that graphene gives unusual band structure at the corners. So in the band structure, we can see that the valence band and conduction band touch at 2 equilibrium points, here and here. Actually 6 equilibrium points all total here in this brilliant zone. So if we suppose we say this is K and this is K prime. So valence band and conduction band, they touch at the at these 2 corners of this brilliant zone, and these are called direct points. Okay, so if we apply magnetic field on graphene, so if you apply magnetic field on graphene at the cones, like at the direct points, electrons and hole degenerate, and they form Landau levels. So at the corner, K at K prime and at K and K prime, electron and hole degenerate and they form Landau levels. Those level can carry quantum information. I'm not sure if this MATLAB code includes. I think it doesn't include spin. Right? So quantum information will not be applicable then.
It can be added later.
It can
be.
Yeah, but because for qubit it needs spin, right? But right now this MATLAB code does not include spin. So here we can see at the K and K prime, this energy dispersion are linear, and electron dynamics can occur at K and K point, K prime. So we know that graphene has a hexagonal lattice structure, as I said before. So this structure can be seen as a triangular lattice with basis of 2 atoms, like suppose here A and B are unit cell. So one unit cell contains 2 atoms, and the lattice vectors here A1 and A2. In the reciprocal space, the reciprocal lattice vectors are B1 and B2. I didn't show how to calculate this, but we know. some of us might know. Now, so if we apply magnetic field on graphene, classically we can use this equation, and after solving we can find cyclotron frequency here. But in quantum mechanically, the Hamiltonian is this. Here, this A vector is for applied magnetic field. It's called vector potential. If we solve here, a Landau gauge is inserted in this equation, and after solving this, we might know that this is, we can solve this equation using separation of variables. After solving this, we get this wave function here. And this wave function describes harmonic oscillator. And you know that energy levels of, this is the eigenfunction of harmonic oscillator, and this is the eigenenergy.
What is U sub n in the second from the bottom? It's chi of y equals U sub n of eta. So what is this U sub n?
Oh, there's some text.
Okay.
This is,
Mhm.
this is how much energy. So these energy levels are Landau levels here. For you know that here n equals 0, 1, 2. Now, this is the tight binding model, tight binding equation for graphene. This term here is for, we go back to the, here we can see this A is one is A, and the nearest neighbor of this A atoms are B, like yellow atoms. And the next nearest neighbors are the same atoms. It's blue. So for the Hamiltonian, the first part is for a nearest neighbor hopping, and the second part is for next nearest neighbor hopping. As here we can see. So this is the nearest neighbor, this part for nearest neighbor hopping, and this part for next nearest neighbor hopping. So for solving this equation, we neglect this part, the next nearest neighbor hopping, and we just consider the first part. So if we solve this equation, we get energy dispersion, this equation. And in this MATLAB code, we consider this T prime, the next nearest neighbor hopping energy is 0 here. So we consider just nearest neighbor. This is the energy dispersion relation after solving the Hamiltonian for tight binding model. And here, this Fk is here.
So this one is a result of analytical solution of tight binding model.
Mm-hmm.
So if one follows from Hamiltonian to eigenstates, one can derive it analytically.
Yeah.
Okay.
And this is without magnetic field, right?
Mhm.
Just
Without
So this E of k is basically this figure on your slide
Yeah,
number
exactly,
4,
this
where
band structure.
6 direct points touch each other.
Yes. This is the figure of Ek
Okay.
after solving the tight binding
So,
equation.
so they just mutually replace each other.
Mm-hmm.
You can use equation instead of this figure, or figure instead of equation.
Yeah. Now, So here this MATLAB code is used for, since it is two-dimensional band structure, it's using for so here we can see this K. It is two-dimensional. It has two components, Kx and Ky. So here, this MATLAB code is here for these two components, this Ky, Kx. So this Kmax is maximum number of K points, 55 here. So for I, this value 1 to 55, and for J 1 to 55. So they mainly represent, I and J represent values for Kx and Ky.
So right after this slide, you may want, well, now it is not here, but you may want to show results of the command mesh of the E plus to check if the formula is programmed correctly. To visualize the variable E plus. When you will be repeating this talk again, at this place you may add figure. Figure to visualize when you run the code, when this variable is set up, this array, you may just mesh in command line and show how this dispersion curve looks like.
Oh, okay. So here is Gaussian wave packet. This wave function is basically for the electron that is on the pi electron. So here wave function for momentum position space, this one, and wave function for momentum space. If first Fourier transform of position space wave function is calculated, then one can get momentum space wave function here. And these are the two wave functions along x and y direction. But I don't know, I have some confusions here. Like if I compare these two equations, I see, I don't know why x minus x naught here.
Okay, you can ask the audience if you...
And why p not x, x minus x naught.
Braden and Jebet must be able to answer. They got highest possible credit in the course based on this code. Just launch discussion. Repeat the question.
So it's time 0, right? I don't know why x. If it is time 0, then it should be only x naught. Why x minus x naught? I don't know.
No, ask them.
Or after time, any time
And
interval?
what
maybe?
point what are they asking about in the equation in the blackboard? Can you use a laser with his finger?
Yeah, this one.
So the initial means time equals 0. So
Mhm.
the initial wave function has to be independent of time, right?
And x
So
after subtimes?
it depends on where you choose your 0 to be. So where you want your wave packet to be centered would be x naught.
If it is time 0, then it should be x0.
Depends on where you choose the original function to be located.
Okay.
X0 is a constant that maybe may correspond to time equals 0, but
Okay.
they're not the same.
Is it sufficient, or you want them to answer more?
No, I think I got it. But why it's dx here? It should be.
That must come from the normalization over the whole grid, right?
So it is
Normalization should be
position of
1.
frame based on the origin.
Listen to them. They will answer correctly. They have certificate.
To normalize the thing on a discrete grid, you need to have the,
Mm.
yeah.
Why?
You need to somehow know your grid size to make the normalization correct.
Okay, this is the grid size. Okay, so I'm confused here. This 55 points is grid size or like key points? It's written that
Number
grid-
of grid points in coordinate space and in momentum space is the same. So the fast Fourier transform is the square matrix.
okay. So in coordinate space 55 for space and in momentum space same 55
Yes.
for key points. Okay.
Yes.
I just noticed that I'm the TV.
Okay, so now it's super tensor thing. There is a new index here, big index. It considers both I and J. And this is the wave function for in coordinate space. Yeah. And this is the wave function in momentum space. And big index here as well, it considers I and J, like both indices here. That's all I can say.
Why this is done? What's the reason for this operation?
For this,
Yes, here you are converting matrix into a vector.
two-dimensional to
One
wave packet to
dimensional.
one-dimensional
Yes.
wave packet.
Why?
To make an array,
To make what?
one-dimensional array.
But why it is beneficial to have one-dimensional array?
I don't know.
Just discuss. We should have a brainstorm. It is beneficial to have 1D array for 2D wave function. Any creative thoughts?
So software architecture? I don't know.
Yes, but it's more comfort of programming. Like, what's the life goal of the wave function?
Stay normalized?
It's a very humble goal, but it's a more ambitious goal.
Get observables.
It's super ambitious. Is there anything in between? If you have dynamics, or if we, what is happening? What people do to wave function all the time?
Propagate over time.
Even if in your idea of finding observables, what do you do to wave function to get observable?
Multiply.
By what?
Probability density.
Yes, but multiply by what?
Factors.
Complex
The
conjugate.
operator, a matrix.
Complex conjugate if you find normalization, but if you find observable, or if you want to find a wave function,
With the square matrix, which is operator.
Jabit is correct. Can you just repeat it and unwrap it in details?
Just in as multiply with the square matrix,
So any wave
making a
function.
sandwich with here.
Yes. So the goal of wave function to be affected by a square operator, right?
Mhm.
And if you are programming, if the wave function is already squared, then it's hard to design operator that will act on it as row by column. Just if one wants to have complete benefit of linearity of quantum mechanics, then it's very linearity, that all equations are linear differential equations. Then it's very beneficial to keep wave function as a vector all the time, and all operators as matrix. Even if they represent multidimensional things, one seeks an opportunity to write down the wave function as a vector and operator as a matrix. And in order to practice it for two-dimensional system, one needs a conversion procedure between number of dimensions that Fatima did present. Make sense?
Yeah.
So when you program your wave function, like it has a certain grid size, but you can't always control that for any Hamiltonian. Is that kind of the idea?
Yeah. In other words, in what cases can't you keep your psi x, psi z separate, as separate vectors, and operate with an observable matrix that corresponds to just the x component or just the y component?
That would be happen when non-diagonal element is 0 for the operator. Otherwise,
I enjoy this discussion, and I prefer question by Braden because it is easiest to answer. So, Braden is asking why this silly operation of transition between square matrix into large vector is important if variables are separated, and one can find all observables related to x and all observables related to y. If x and y, dependence on x and y are separable, if one can write wave function at each point of time as wave function along x times wave function along y, then you are correct. But if if it is two-dimensional box or two-dimensional oscillator, but if x and y are not independent variables, if it is like a coupled pendulum with 2 points and then spring between them, and separation of variable is more complicated, then x and y are not independent variable, and one needs to have two-dimensional structure. And then this shortcut that you offer in game will not work.
I see. Yeah.
Good?
Yep.
Should I answer questions of Aaron and Jared?
No, we keep.
Okay.
So here, we know that if we apply magnetic field on graphene, then electron, that pi electron, will have circular motion, and that electron will have angular momentum. So it will experience Lorentz force, and it will move in circular motion, and it will have angular momentum. That now this angular momentum was r cross p, and the rest of the things like it's just determined, and everyone knows this. So yeah, and here 3 operator layers, 3 components. So in MATLAB code, this angular momentum will there will be code for an angular momentum.
And what is the energy of interaction between electron that is already circling with some non-zero angular momentum and magnetic field? What is energy of interaction between magnetic dipole and magnetic field? And we all are colleagues helping each other. If anyone wants to.
You are talking about Lorentz force? No, energy.
Lorentz force, if you characterize a particle with a vector of velocity, and we do not know where it will be, but if it already quantum particle going on some certain pattern of motion, and one knows that for this motion there is a value of angular momentum. If it is coiled with a current, right? What is the energy of interaction between magnetic dipole and magnetic field? Do not hesitate to cast it, to pronounce it if you're aware. I don't know what was the list of courses in physics, but I assume that Braden should have went through it several times.
Should should be like minus the inner product of the dipole and the magnetic field, right?
Maybe with minus sign.
Minus the inner product.
Magnetic dipole and magnetic field. You agree?
Magnetic dipole. I don't know. I don't remember now.
Okay, and what is the magnetic dipole for quantized electron that moves in the orbit? Is there a connection between magnetic dipole and the value of angular momentum?
Should be related to the core magneton at that time.
Yes. So angular momentum times magneton will be the magnetic dipole. So interaction between electron and circular orbit and magnetic field will be dot product between magnetic field vector and angular momentum vector times some constants like core momentum at minus, right? What if the magnetic field is aligned along z-axis and rotation happens in xy plane only?
The maximum.
Yes, and one can, instead of dot product, one can multiply the z projection of angular momentum times z projection of magnetic field, because anything else is zero. So one needs, and if one doesn't know the orbital trajectory of electron, one can promote this relation into operators. Like instead of vector potential, one can make interaction between magnetic field and electron as product of angular momentum operator and value of projection of magnetic field in the direction. No one.
Is it something like Pauli spin matrix, something like that?
If we want to do like NMR spin rotation and everything very precise, one can do. But here we have only angular motion for that. We do not care about spin. So the source of magnetic dipole is just physical rotation of electron on the trajectory.
So here we see this Hamiltonian. I'm not sure exactly what happens.
But
what's going on.
try your best and we'll continue
So
brainstorming.
here Hamiltonian, I know that spin is neglected.
Huh?
So here Hamiltonian, and it is here in this part of code it makes a super tensor, super matrix.
Okay.
4 indices into 2, converted to 2 indices.
For the same reason why we converted wave function from 2 indices to 1 index.
Yeah. And unity, it's for delta function. But I don't know why it should be delta function here. Like why Hamiltonian should be.
Okay, tell the best you wanted you can, and I'll add a comment we all will discuss.
So here we can see that of this Hamiltonian and the product between Hamiltonian and unity. So here it's a diagonal matrix. I see this in so diagonal matrix here. This here. I don't know, I'm lost here.
No, you're not lost. You're presenting everything in a perfect way. Let me contribute quickly and then you continue. Just stay here, I will just make one quick note. John Swenson, if you are watching this recording, this note is for you. So, we do have Hamiltonian that affects indices related to x, and we have the same Hamiltonian that affects indices related to y, right? Right now, before we switch on magnetic field, there we can apply shortcut and trick offered by Braden. So we do have Hamiltonian affecting x, and we have Hamiltonian affecting y, and we have some indices like I1, J1, but there are two terms: Hamiltonian that affects x dimension and Hamiltonian that affects y dimension. There should be plus between them, but what happens? Suppose we have this psi of x, psi of y. Can we directly act with Hamiltonian that affects only x variable on this product? Is there incompatibility of dimensions?
So that's why you need it.
So when it's to, like, if there is I1, I2, here we have I1, J1, and one needs to add delta I2, J2. So the Hamiltonian that acts on the first dimension must be multiplied by delta function, which is formally reproduces the same dimensionality as if it would act on the second dimension, but it changes nothing in a second dimension. So we need to hx I1, J1, delta I2, J2, plus delta I1, J1 times hy I2, J2. And this idea is implemented in the line right here.
So here, if I equals j, then 1, otherwise 0. So there will be no y. A Hamiltonian for x first term, and then Hamiltonian for y second term. Okay. Sounds good.
Any comments, protests, complaints, suggestions? Would you accept this? Thank you.
And here it introduces this thing like angular momentum.
And it has the same structure. So two terms,
Exactly.
and each term is product of two. Is x operator related to coordinate operator related to x dimension times derivative operation related to second dimension, minus derivative operator related to x dimension times position operator related to second dimension. And this term will mix x and y and make them non-separable. Also, what is written in the frame is related to angular momentum operator in coordinate representation. But one can do the same thing, everything in a similar way in the momentum representation. Right? So one can express position operator in momentum space and momentum operator in momentum space.
It would look very similar though, wouldn't it?
Mm-hmm. Yes, yes. And it is 1, 2, 3, 4, 5, 6, 7, 8 lines lower, so it is the operator angular P.
Yeah, what is angular P here? what's the difference between angular and angular?
Mhm. So angular is angular momentum expressed in coordinate space, and angular p
Oh,
is
yeah,
angular
it's
momentum in
space,
momentum
yeah.
space.
Mhm.
And momentum space is needed because we want to import dispersion curve, which is also already set up in momentum space. There is no coordinate there. And then do dynamics in momentum space rather than coordinate space.
And then this one big Hamiltonian for big indices. That's
Mhm.
why. Okay, and then why it's direct here?
Because it relates to, it will include Dirac cones, and it directly imports the dispersion that you explained several slides before.
Okay. Yeah.
Can you one slide back? So, and after your big Ham Dirac, we can go one or two lines lower. So it shows play Ham is no two lines lower. Play Ham Dirac is
Big Hamiltonian direct plus angular momentum.
yes. And then right now it is blocked by this video frame, but
Mhm.
it's also multiplied by negative magnetic field. So it's Hamiltonian that set up from the dispersion curve times a term that will mix x and y dimensions in momentum space.
So you're assuming the structure of the dispersion, and then you're just doing this thing on top of it.
Yes. So not changing the dispersion, but just moving on the dispersion curve, same as we move on the potential energy surface.
You don't allow it to react to anything. It just is.
Mm-hmm. Fatima, I'll just give a brief comment to Braden. If there is no magnetic field, if there is no additional perturbative term, which may not be perturbative, may not be small, the momentum is conserved. And any initial state in momentum space will stay unchanged. But magnetic field is the reason to change momentum. Make sense?
Here all I can say that it's propagator in coordinate space, this G tau. Yeah, I don't know, I have no idea.
You do. You know the evolution operator and least action principle, right?
Yeah, I know, but
Okay, good. Right. And the same evolution operator in the momentum space.
this is for coordinate space. Right? Yeah, this is for momentum space.
One slide back. So what is here?
E tau, I think it's evolution.
If you want, you can explain each line, but we need basically only the last line.
The last one is for coordinate space. Sorry.
But what is this product? Just how to interpret it? Like which equation would you add if you need to explain it not as code but as equation? show it. So what is being computed here is propagation of the wave function from time t to time t plus delta t, right? And for this small increment of time, it is evolution operator is Hamiltonian minus magnetic field times this angular momentum times delta t. So this stuff in yellow is big G tau. The stuff in blue is this big psi, and another big psi, which we can circle in other color, is wave function at previous time. Okay.
Oh, that was the.
Okay, and what's that?
Here again, the big index. Like this big index includes two indices, I and j. For that.
Oh, so you return back from the vector form into matrix form
That's what.
for visualization, right? At the beginning you went from two-dimensional form to one-dimensional, now you return to two-dimensional.
One-dimensional to two-dimensional.
Uh-huh. Okay.
Yes. So I j. Okay.
And then there is a probability distribution that Aaron mentioned. So it's like 1, 2, 3, 4, fifth line from the bottom. Like probability P xy and probability 3 xy. And those things can be plotted at each point of time to see what happens. Right? Maybe just escape and restart. Oh, okay. So it is in momentum space. And this one is in coordinate space. So the motion in coordinate space is not a surprise, but in momentum space it is expected to stay unchanged, and it makes some motion. No thanks. Same question as to David. What is the main observable, and what is your strategic plan of further calculations? What are you going, like this is, you presented instrument, and now you need to use it. Which data are you going to generate?
I think I need to put the magnetic field, value of magnetic field,
Uh-huh.
all the values, and then see what happens.
Okay, and what will be the outcome? Are you going to just make like several dozens of such images, or there is some way to summarize this motion into a number? It's a tough question. I don't know the answer. You may consult with the audience.
Only using this MATLAB code? No.
Well, you are the author. You may modify it as you wish.
So if there is, for magnetic field, I don't know.
No, I don't know is not accepted.
So
What's your plan? What, as a researcher, you want to extract out of this setup? What seems reasonable? Ways what?
oh yeah, it should be momentum resolved dynamics.
Okay.
So how this motion is influenced by momentum, number of K points. Momentum. That number of K points will be about 55 there.
In your image, what is plotted on the top of the panel?
Here,
Yes.
probability density. No, you mean
Oh yes, yes. But what are the numbers on the top?
magnetic field time,
And
momentum in X direction, momentum in Y direction.
which momentum in X and Y direction?
Which momentum?
Uh-huh.
It's in momentum space, I mean in reciprocal space.
Yes, but what are these numbers?
K values.
At what time? At what time is it those?
Let's go to the slide number 12. The one you were consulting with Braden.
Which one is to
Back.
This one?
More backwards. More backwards. More backwards. This one. Yes. So those, what is P not X and P not Y? Can you point them and explain what they are?
P naught X. It's momentum at when time equals 0. At the
Yes.
starting point.
Yes.
X direct. X component of momentum.
Yes.
Mm-hmm.
So, do you think the dynamics may depend on the choice of this initial momentum?
Sure.
Would it be interesting to check different values of initial momentum and see how the trajectory and maybe...
Mm-hmm.
So let's go to your last or second last slide with this probability distribution. So,
This one?
no, yes. So, where on the image, this yellow image, can you point by laser pointer where are these values of P sub X of 0 and P sub Y of 0? Yes, it is a center of this Gaussian wave packet in momentum space. What if the initial momentum will be 0? Px not will be 0 and Py not will be 0. How this trajectory will change? Like if your equation is Lorentz force, if initial velocity is 0, will be there any dynamics? Will be there any change to velocity?
No.
So one may expect that if one starts in the center of this diagram, there will be nothing changing,
Mm-hmm.
right? But as far as you set up different values of initial momentum, it moves, it interacts with magnetic field more and more.
Yeah, but here is initial value, right?
Initial value, but you can run the code like 200 times with different values of this P naught and see how the result, how the
No,
outcome.
like Px and Py is 0 here.
Yes.
Still it's running. Still it's moving, like we can get the wave packet.
Yes, but right now you choose, there are some non-zero numbers, right? Px at time equals 0, py at time equals 0. In the brackets it's initial time, right? Time equals 0.
Okay. So you mean px equals 55?
Uh-huh.
Who's that?
It should be somewhere at the very beginning of the code, at the first
Oh,
lines.
yeah, but I'm looking at this figure.
Maybe it's some scaling factor. So it
And
is.
this figure looks like it's 0. Right?
No, it's not 0. It's
Because 0 is this way, and this.
but it's slightly away from 0.
Oh,
Okay.
no. So the center should be at the 0, right? If
Right
it's
now,
0, right now it's
yeah,
not.
center is 0, and
Okay. So
initial.
the center is 55 minus 55 right now, but it doesn't look that it is.
It could be a
55.
scaling factor between axis labels and the values.
Mhm.
Question.
Yes.
So I'm confused how this ties into the original statement about like a graphene lattice.
I'm with you. The results presented in this single image, single slide with results, are made for score dispersion without input of the graphene dispersion. If graphene dispersion is inserted, the dynamics will differ from just circular motion. It will be something much richer.
So this is just a free particle.
Yes, yes, free particle field. So it's like instrument is ready, but it's 90% of work to run it again and again and analyze the data.
So this one is not for any particular model, just for electron in one carbon atom, or
No, it looks like free two-dimensional space with the results that you are showing right now.
so graphene sheet. I mean, not
No,
quantum.
it's even not a graphene sheet. This one is like free space.
Free space, not graphene.
This one is not, no, for graphene it should look differently. We may talk more why it did happen, but I recognize this as a signature of free space. For graphene, it will be stuck near these direct points and maybe form some patterns, oscillations, and jump like tunneling from one direct point to another one. It will be more complicated motion.
So right now,
It's a good effort, but it is not yet the results
so
for.
this code should be modified for graphene.
No. The code is it should be run. All components are there. Maybe it's just one symbol, one line to move the comment out % somewhere, and we may discuss it. It's easy thing.
I don't know. I'm confused. Like I was talking about the graphene all the time, and finally MATLAB code is not for graphene.
The code is for graphene, but the results that you're presenting were generated for.
Is it possible to modify for graphene this code?
Yes, the code you're using is for graphene.
Okay.
And you did a great effort of presenting and analyzing how this instrument is working.
Okay, so what I understand for graphene, this code needs to be modified.
Just one line.
One line, okay.
But when you were generating these movies,
When
yes,
you generated the,
No.
I got it.
you cannot tell this. When this, I'll ask differently. When these movies were generated, with which version of the code did you run the latest version of the code to generate the movies for today's presentation?
Like that's what I'm talking. Like
Huh?
I tried to run this code and I got video. It did not work. Then I asked you to provide me That video.
But it was like a couple of months ago. You need
Yeah,
to run the
that's the thing here.
You need to run the latest version.
I didn't run it.
Please do.
Okay. I was just busy to like understand the code, how it.
And you
works.
did a great job. Okay, let's thank Fatima. Other more questions or discussion points?
Do you see Landau levels if you let it run for long enough? Or do you see like a circular eigenstate for your real space? Like if you played that B movie for long enough, does it make like a
like in this movie, you mean?
right for B? Like it seems like it kind of stops short, but if you extended like the time that it ran, does it actually form like a pretty tight sort of uniform ring motion? Like if you kept going for another 1,000 steps.
Aaron, are you asking if it'll like localize to a ring instead of be spread out?
Right. Or at least like some of the weight packet anyway. Because you'd expect, like on your slide 7, if you just put in all the equations, you expect like circular motion of your particle.
Mm-hmm.
And it should have like a certain frequency or
Mhm.
integer number
Mhm.
frequency.
Mm-hmm.
So it's like you might just have to play with initial momentum values enough for it to stabilize or for it to find the right settle into that state. That's just a guess though.
Fatima, you can answer no. Say no.
No.
It's a really deep, serious, and good question for analyzing, but the answer is no in the following sense. The Gaussian wave function, which is chosen as initial state, is not an eigenstate of this Hamiltonian. Therefore, any dynamics will be composed as superposition of eigenstates, but will never come into an eigenstate. It will be always some dynamics. If one would program initial state as Landau level, it will be a stationary and it will not change in time. There is a chance to answer your question in the following way. When the Hamiltonian is set up, one can always practice the eigen value and eigenvector. Just find eigenstates of the Hamiltonian in a like, silly direct way. Then try to convert these eigenstates into this two-dimensional distribution and see how they look like. And there is a big hope that they will look like Landau levels. Although with programming and human factor errors are sitting, there is a chance of errors everywhere. You approve this discussion?
Yes.
You approve this discussion? Aaron was checking, like in your introductory slides, you were presenting Landau levels, and the question was: is it possible to illustrate Landau levels with this code? And just by running it in its current form without modification, it will be never Landau levels, because it's Landau levels are eigenstates, and the code is made for non-eigenstates for some motion. But if one just takes Hamiltonian that is already set up with magnetic field and diagonalizes it, one can hope to get Landau levels. Very good discussion. More questions to Fatima? More points of discussion? If no, let's thank the speaker once again. Thank you for being very brave. It's a very hard topic that everyone fears of.
Oh, the MATLAB code is not programming. There's
I
the
hope you
thing,
I hope you didn't erase your. You didn't close.
What?
You didn't close because there were some notes we made.
Oh yeah, I did.
Okay, well, thanks much for investing your time. Meeting is dismissed. Have a pleasant Thanksgiving, and there is a hope that we'll discuss one-to-one who will be presenting next time. But it will be really good if we target Sunnyvale, although it is hard to arrange with fund issues, but it's very beneficial meeting. Okay, done? And have a nice night. Thanks.